of it is full of hydrogen. And the land is full of carbon, especially on top where things grow. But until recently, only nature knew how to combine these elements into polyisoprene, the natural rubber molecule. We find these molecules in a milky fluid known as latex. Nature produces it inside a tree. Why? Nobody knows. But centuries ago, some Indians down in what is now South America discovered that the latex was in there, and that if you slashed the tree, it would come out. And that if you smoked the stuff over an open fire, it would become a resilient substance that would stretch and bounce. And there the matter rested. Centuries later, it got its name. Early scientists, wizards really, just beginning to back away from the practice of magic, found that you could use a piece of the stuff to rub out pencil marks. They called it rubber, and the name stuck. Trouble was, so did the rubber. In warm weather, it got soft and sticky, and in cold weather, it got hard and brittle and would break. That's where things stood until 1839, when a man named Charles Goodyear discovered that by the addition of sulfur in a process which he called vulcanization, rubber became more lastingly resilient, strong, exciting, and useful. And around the turn of the present century, it made the automobile practical, or at least helped. And since then, rubber not only revolutionized America's agriculture, but also became indispensable to the development of motor transportation, the airplane, and thousands of other things. There's something else nature did a couple of million years ago. She shoved a lot of greenery and assorted animal life containing carbon and a lot of moisture containing hydrogen far under the ground. There it was squeezed and compressed unmercifully. And among other things, what that did was to produce oil, which is made up of a whole family of the kinds of molecules we call hydrocarbons. A hydrocarbon is any molecule which has only hydrogen and carbon atoms in it. It's impossible to say just how many different kinds of hydrocarbon molecules there are, because there seem to be just as many different hookups of these two atoms as man and nature working together can manage to contrive. For example, we know that there are substances called catalysts, whose atoms or molecules are quite willing to serve as our temporary agents, as a kind of tiny task force dedicated to getting in there, unhooking atoms, and hooking them back together again in a new way, so that the resulting molecules will still contain only carbon and hydrogen atoms, as a good hydrocarbon should. Man's ability to produce new hydrocarbons or to reproduce hydrocarbons made by nature is limited in part by his knowledge of catalysts and what they will do to what mixtures of hydrocarbons under what conditions of temperature and pressure. And the only way to find out is to try and try and try again. Because nature, while it is quite willing to be spied upon and does everything quite openly, has never been known to volunteer an explanation of any of its behaviors. During World War II, the United States, where rubber trees do not naturally grow, found its supplies of rubber from elsewhere rapidly sinking out of sight. But the United States did have plenty of hydrocarbons on hand, coming out of holes in the ground. And a good supply of scientists who had been inquisitively trying to find out for several years how to turn petroleum hydrocarbons into isoprene hydrocarbons, the natural rubber molecule. Suddenly, those scientists and technicians became very important men indeed. While all through the war they never did find out how to make natural rubber synthetically, they did discover rubber substitutes, And importantly, they learned and taught a whole industry of engineers and technicians how to build and operate a kind of synthetic rubber tree for producing synthetic rubber-like substances in tremendous quantities, using petroleum hydrocarbons as the basic raw material. From the beginning of the synthetic rubber industry, the most widely used material has been known as SBR, an abbreviation for styrene butadiene rubber. Both styrene and butadiene, the basic ingredients, are made from petroleum. In modern chemical plants, these petroleum byproducts are combined to form synthetic rubber latex. It is coagulated by acids, washed, dried in huge ovens, and packaged in compact bales for more efficient handling. The American synthetic rubber industry expanded from practically nothing in 1941 to 450,000 tons a year by the end of World War II, and to nearly 550,000 tons by 1950. By 1955, the United States was producing 900,000 tons a year. Since that time, its production capacity reached and exceeded the magic figure of 2 million tons a year, surpassing the total worldwide production of natural rubber. Although many different types of synthetics were developed, some actually superior to natural rubber for specific uses, in certain other critical applications, none had the special properties to replace natural rubber completely. What are some of these special properties of natural rubber? Well, this is one of them: its extraordinary resilience. Compared to most synthetic rubbers, natural rubber has far more springback. Another of natural rubber's unique properties is its excellent resistance to heat buildup. For example, if you bounce a rubber ball made of ordinary synthetic rubber, you will find that its rebound distance is considerably less than a ball made of natural rubber, and that it gets hotter in the process. The reason? More of its rebound energy is being converted into heat, while the greater inherent resilience of the natural rubber ball prevents this energy from being dissipated into heat. A vital application of this principle is found in heavy-duty truck tires, where high heat is generated. Only natural rubber, with its excellent low heat buildup qualities, has been satisfactory for this grueling application. Tires for today's jet aircraft with high-speed takeoffs and landings under tremendous loads also require natural rubber's high tensile strength and flexing qualities. This is probably the most common and most widely used of all rubber products. Until 1962, only natural rubber with its high elasticity could be used to make a good rubber band. Another advantage of natural rubber is its suitability for certain manufacturing operations as well. It is not only the end use of this hot water bottle, for example, that causes it to be made of natural rubber. The hot tear resistance of natural rubber is essential to the production operation itself, so the mold can be removed from the neck of the bottle after curing. So unless and until the man-made equivalent of natural rubber could somehow be duplicated in the laboratory, dependence on the rubber tree would apparently continue to be an industry requirement for years to come. But scientists never stop being inquisitive, whether there's a war on or not. And eventually the catalysts, combinations, and conditions which would produce a whole new class of synthetics were discovered. They are synthetics in the sense that the trees they grow in are man-made structures. But one of these in particular can hardly be called a rubber substitute, because its molecules are arranged in exact three-dimensional order, just like the molecules of natural rubber. The chemist's name for this new synthetic is polyisoprene, the duplicate of natural rubber. Another of these stereosynthetics is polybutadiene, which in some respects might even be called an improvement over natural rubber. These new synthetics are called stereo rubbers because of their three-dimensional configuration. And the raw material supply for both of these stereo rubbers is not somewhere else, it's right here. Petroleum is the basic raw material. To make polyisoprene, the synthetic twin of natural rubber, the petroleum is separated into several parts, some of the parts being gas oils. The gas oils are then fed through catalytic crackers and broken down into light hydrocarbons containing, among other things, propylene. This is concentrated by distillation. Then, through an exact chemical process, the propylene is converted into high-purity isoprene. The isoprene is mixed with solvent and then charged through a pipeline into huge pressurized tanks called reactors, where a process called polymerization takes place. This occurs when the catalyst is added, starting an immediate reaction that causes the molecules to join together in precise three-dimensional arrangements. When the desired degree of polymerization is achieved, the isoprene molecules have become polyisoprene, or natural rubber. It is a thick, viscous liquid and is drawn out at the bottom of the reactor. At this point, a stabilizing agent is introduced to deactivate the catalyst. The polyisoprene then flows into a hold tank. An antioxidant is added to protect the rubber, and then in solution it is subjected to a devolatilizer, a steam bath which drives off the solvent. The rubber, now coagulated into crumbs, flows off in a hot water slurry. It is then sent through a series of dewatering and drying machines up a spiral conveyor and on into the baler. Here it is formed into easy-to-handle bales of rubber. The bales of rubber are then wrapped and ready for shipping. On a 60-acre site, this single plant produces as much of these new stereo rubbers per year as a rubber plantation covering 45,000 acres with 5 million trees. It takes a rubber tree at least 5 years to start producing rubber. This chemical plant does it in a matter of hours, a spectacular testimony to the ingenuity of rubber industry scientists. Isoprene converted from propylene is the principal material used in producing polyisoprene. However, isoprene must be extremely pure, and a method of making large quantities had to be developed before polyisoprene rubber could be produced economically. This plant makes its own isoprene from propylene, which is piped in from a nearby oil refinery. In a series of catalytic processes, the propylene is converted into isoprene. Before this isoprene can be used for making rubber, it is highly purified in these 200-foot distillation columns. From here, it flows to the reactors in a continuous stream. The catalyst, along with the solvent, is introduced also by pipeline, and polymerization starts immediately. By its very nature, the catalyst for making polyisoprene rubber is highly reactive. It cannot be exposed to air, or it will burst into flame. Polymerization of isoprene to form rubber is carried out under precisely controlled pressures and temperatures. It is then pumped into a vessel containing boiling water, where steam drives off the solvent, leaving the rubber in a crumb form. The moist crumb rubber then travels along a separator screen and into a moisture expeller. In this operation, moisture content of the rubber is reduced to 10%. This is accomplished through a heating and squeezing action. The remaining moisture in the rubber is then removed by passing through an extruder dryer machine. A spiral conveyor literally shakes the rubber particles upstairs to the top of a huge baling machine, where it falls into a baling cavity. When the cavity is filled with just the right amount by weight, the rubber is squeezed and compressed under tremendous pressure to form a bale weighing about 80 pounds. Each bale of rubber must be wrapped, and this too is done automatically. A sturdy, non-sticking plastic film is used. This wrap is tightly sealed, like the loaf of bread on the grocer's shelf, and protects the rubber during storage and shipment. From start to finish, this synthetic duplicate of natural rubber is produced in a matter of hours, under carefully controlled conditions. Stereo rubbers are made from precise formulas. Electronic controls provide instantaneous command over every phase of the production cycle. Formulas, temperatures, time cycles must be exact. Scientific instrumentation eliminates all guesswork. A fully equipped laboratory is an essential part of the stereo rubber plant. Continuous checks and analyses with modern testing equipment are used to determine quality. The raw materials, the various chemicals, as well as the finished rubbers must meet specific standards. The rigid tests made by these technicians are the guideposts for the operation of the plant. Production of polybutadiene rubber is similar to that of polyisoprene, except the raw material is a ready-to-use petroleum byproduct, butadiene. Time required for polymerization is much less. Actually, it's done in minutes. But the end result is similar in that we get a synthetic stereo rubber having an orderly, controlled, three-dimensional molecular structure. Polybutadiene blended with other synthetic rubbers makes a remarkable abrasion-resistant substance with quality improvements even nature might envy. Its abrasion resistance has been proven in rugged laboratory tests, such as this one. While the rugged dynamometer test, used to determine the limit of tire durability, has time and again revealed the outstanding performance of polybutadiene in tires. These tests have not been confined to the laboratory either. Test track operation has reinforced this data in performance as well. And now there is added testimony from the grueling arena of the stock car race, where only recently cars using synthetic rubber in their tires have begun to zoom into the winner's circle for the first time in stock car history. More dramatic proof of polybutadiene's outstanding durability could hardly be found. No question about it. Polybutadiene rubber, when blended with either natural or other types of synthetic rubber, gives many additional miles of safe tire life. It improves aging properties, increases abrasion resistance. Passenger tires made with certain polybutadiene rubbers give longer tread life and have greatly improved body durability. While its primary use is in tires of all kinds, the service life of conveyor belting and other products subject to harsh abrasive use is greatly extended by polybutadiene. The same is true of play shoes for children and other consumer items demanding the toughness to resist the severest wear. But the real hero of this breakthrough is polyisoprene itself, the synthetic equivalent of nature's own naturally grown molecule. Unlike polybutadiene, polyisoprene rubber need not be blended with any other material. It is real rubber. It can be processed in the same manner as natural rubber. Its characteristics are the same, and in some ways better than natural rubber. Like polybutadiene, it has faced and withstood a great battery of laboratory tests. Tests that measure its tensile strength, its abrasion resistance, its resilience and flexing characteristics, and its ability to recover from repeated stretching. In every case, polyisoprene has equaled or exceeded the limits for natural rubber. This remarkable chemical equivalent of natural rubber has other advantages as well. Shipping operations from chemical plant to manufacturer are faster and more economical than those required to bring crude rubber stock from remote areas of supply overseas. On arrival at the user's plant, unit containers holding 33 clean and uniform bales of polyisoprene, each weighing 80 pounds, can be handled much more quickly than the bulky, irregular 250-pound bales of tree-grown crude rubber. These units can be stored in a minimum of space, and with polyisoprene there is no need for costly preheating, cleaning, or preliminary cutting, as is the case with natural crude. When the manufacturing process begins, each compact bale of polyisoprene can be removed from the container and thrown directly into the Banbury mixer. Further processing time on mills is greatly reduced with polyisoprene. So too, in many instances, is the rate of extrusion, as proved in the laboratory. But as always, any new material stands or falls on its performance in end-use applications. And since it is an exact molecular duplicate of natural rubber, polyisoprene can be used as a 100% replacement for tree-grown rubber in practically all applications. From squeegees to basketballs, erasers to insulated gloves, grinding wheels to safety vests and ski clamps, from textile applications to adhesives, from golf balls to hip boots, polyisoprene is a first-team replacement in any product or application where natural rubber has been indispensable. Sometimes the requirement is for high tensile strength and soft resiliency, as well as heat resistance to withstand repeated sterilizations. Until the development of polyisoprene, only natural rubber was deemed satisfactory for use in this important application. Surgical tubing, rubber thread, bathing caps, washers, rubber stoppers, footwear, all represent important uses for polyisoprene. In fact, as our technology continues to grow, polyisoprene will find its way into a myriad of exotic new uses. In applications that rival the vastness of the universe itself. Already, for example, the prototype of this proposed space station exists and is being studied and tested by space scientists. Made of inflatable, rubberized fabric, it can be shot into orbit in a small capsule and then be inflated when in position. Here in space, one day soon, such man-made materials as polyisoprene will be waiting for the men from Earth who follow, waiting to be inhabited for a time by the pioneers of space on their way to more distant bodies. By no stretch of the imagination could Charles Goodyear, in 1839, have foreseen this kind of application for his vulcanized rubber product. But he would have recognized a kinship. The pioneers of space, depending for survival on the pioneers of rubber chemistry, scientists dedicated to making the products we need from the natural resources we have. Freed of their dependence on the rubber tree, they have just begun to explore the many uses of polyisoprene for all the world and beyond.